Hello, my name is Dylan Olszewski.
My name is Alex Chindris.
And I'm Jack Million.
We're Team 1093, and we're from the Episcopal School of Jacksonville High School in Jacksonville, Florida, coached by Andy Hostetler. We're doing Problem C, Standing Against a Mammoth. We hope you enjoy.
The Clovis point attached to the end of a stick was a common weapon of choice for ancient humans. While we know that they had these spears, we aren't sure how they used them. Either they would throw the weapon at the target, or they would have the animal charge at them and brace for the impact. While we can't really know for certain which approach they took, we can use mathematical modeling to compare the scenarios. In this presentation, we will present why we think the bracing method is more likely to have been used, as well as what kind of spear designs would be better for throwing as opposed to bracing.
All parameters and variables are measured in standard SI units. Note that the reference area, capital A, refers to the surface area of the spear being affected by drag due to air resistance. Also note that the drag coefficient, C sub D, has no units.
Our key assumptions include that the spear is assumed to travel in a straight horizontal path, unaffected by gravity. Throughout the spear's path of motion, there is no angular velocity acting upon it. The momentum is conserved during all collisions. The spear will never break. All points of impact on the animal are equal for the purpose of evaluating lethality. The friction of the ground is assumed to be zero. The spear is assumed to travel through air at sea level, meaning we have a rho value of 1.225 kilograms per meter cubed. The mass of the target animal is assumed to be 200 kilograms. The drag coefficient will remain constant for all values of velocity, and that the mass of our human is 75 kilograms.
The lethality of an impact is defined by the sum of all the force applied to an animal. This is also equal to the change in momentum, so we can use the law of conservation of momentum to derive an equation for lethality. The equation boxed in blue represents the lethality of the bracing scenario, and the equation boxed in red represents the lethality of the throwing scenario. This graph represents lethality as a function of impact velocity, and the curve of the bracing scenario is significantly steeper than the curve of the throwing scenario. A thrown spear must be traveling significantly faster than a charging animal to generate the same amount of lethality. This is because a braced spear benefits from the mass of the human holding it.
In order to derive an equation for the final velocity of the thrown spear, we start with the formula for drag force. We have chosen to use h to represent the quantity coefficient of drag times rho times capital A over 2 for conciseness, as this quantity shows up frequently in our derivation. Next, using Newton's second law as well as the formula for the drag force, we can come up with an equation for the acceleration of the spear. Next, because we know that the derivative of velocity is acceleration, we can integrate our formula for acceleration to get velocity. By using that same logic, if we integrate again, we come up with an equation for the position of the spear. Next, by solving that position equation for time, we can plug in the total distance the spear travels d into position to give us the final time. Finally, by plugging in that final time into our equation for velocity, we are left with an equation for the final velocity of the spear. The next graph shows the proportion of velocity lost due to drag over spears of varying reference areas. From the graph, we can see that as the reference area of a spear increases, the proportion of velocity lost due to drag also increases. Or, to put it simply, spears with greater areas experience much greater effects from drag. This graph shows the proportion of velocity lost due to drag over spears of varying masses. As we can see, as the masses of the spears increase, the proportion of velocity due to drag decreases exponentially. Or, to put it simply, as the mass increases, the effects of drag decrease significantly. The final graph shows the proportion of velocity lost due to drag over spears that are thrown varying distances. As we can see, as the spear is thrown longer and longer distances, the proportion of velocity lost due to drag increases. Or, to put it simply, as the spear is thrown farther and farther, the effects it experiences from drag increase.
Ancient humans likely braced their Clovis point spears rather than throwing them. This is due to the fact that when they are thrown, spears don't have the mass of the human to back it up. As a result, the spear needs to be thrown very fast to match the impact of a charging animal in the bracing scenario. In all situations, spears with greater masses will yield greater lethality. A good throwing spear will reduce the velocity lost to drag the best. As a result, the Clovis point is not the best throwing spear. Something like a javelin, which has a significantly smaller reference area, would be the very best for throwing.
We believe that our model is effective in terms of examining spears of varying masses and reference areas, and that it also accounts well for the effects of air resistance, which allows us to optimize fairly well for a thrown spear design. Our calculation for lethality is simple and effective, allowing us to easily compare the differences between throwing and bracing a spear. And our proportional value for velocity lost to drag provides a concise value to analyze the acceptable amount of drag for an ideal throwing spear. We also fail to take into account any varying resistance experienced by the spear as it enters the animal in different parts, as we just assume that the resistance is equal everywhere. We also didn't get to implement our more advanced model of lethality, which takes into account the displacement of the animal's flesh upon impact for a given spear design. Thank you so much for spending the time to listen to our presentation, and we sincerely appreciate being offered the opportunity to learn about derivative modeling.